All right, thank you for joining us today. And in this video, we are going to learn how to differentiate different functions like polynomial function, radical function, exponential function, natural log functions, that is the len function, and then we look at the log function itself. Right. So let's jump right in. So we started with the idea of the properties or the rules of what derivative, right? And we learned that this was the power rule. And then the power rule is actually for polynomial functions, right? So if I have a polynomial function, then all I need to do is to use the what? The power rule. And we also learn how to convert the radical function in the form of the power rule so that we can also use the power rule to what? Solve, right? So this, I think we've done it already, but I just wanted to show you how to differentiate a polynomial function and what? A radical function using the power rule, right? So this is what we are going to do. This is what we are going to do. Now we know that from the power rule, this y prime here, our y prime, our y prime, our y prime is going to be n drops down, we maintain the function, and then we subtract 1. So all polynomial functions, we use the what? The power rule to what? Just differentiate it. So this is like the power rule. N drops down, you maintain the function, then you what? You subtract 1. So that is how we differentiate a polynomial function. So the example that we have here, this one is a polynomial function of degree 3, right? So all we need to do is we need to apply the power rule to what? Differentiate this. For the radical, what we just need to do is this can be written as x to the power 1 over n, right? And this will form like the power rule, like in the form of a polynomial function, right? But not a polynomial function because this is not a whole number, right? It's a fraction. So what we are going to do now is now we are going to look at the idea of differentiating this function right here. So this, we are going to use the power rule, which is going to give us 1 over n drops down, we maintain 1 over n, then what? We subtract 1. So same idea of differentiating, the same idea that we use to differentiate what? A polynomial function, right? So this is a polynomial function. This is what? Also a radical function. So when you have a polynomial function, think about the what? The power rule. When you have a radical function, try and convert it to x to the power something and also try using the power rule. So let's look at these two examples right here. Now A, we want to differentiate f of x. So now we see that this is a polynomial function, so we need to apply the power rule, right? So applying the power rule, when I differentiate x to the power 3, I'm going to drop the 3, then I'll maintain x to the power 3, but I'm going to subtract 1, plus, now we just learned the constant multiple rule, right? So I need to bring out the 2 because the 2 is multiplying the function. Then I need to differentiate x to the power 2. So 2 drops down, 2 minus 1. And then we learned that when I differentiate a constant, I'll get 0. So this is going to give us 3x squared plus 4x plus 0. And then it's just 0. So this is what you are going to get for differentiating a polynomial function. Let's look at the last one here. B, we want to look at g prime, but first what we need to do is we need to try and simplify it, right? From this side to this side. So let's try and simplify this function before we differentiate. So root of s can be written as x to the power 1 over 2. Cubic root of s can be written as x to the power 1 over 3 plus 1. So now that you are done with the simplification, then we take the derivative. Now power rule, 1 over 2 drops down. We maintain 1 over 2, x to the power 1 over 2, but we subtract 1, plus 1 over 3 drops down. We maintain x to the power 1 over 3, but we subtract 1, plus when I differentiate a constant, I get 0. So what are we going to get? 1 over 2. 1 over 2 minus 1 is minus 1 over 2, plus 1 over 3. 1 over 3 minus 1 is minus 2 over 3. So this is what we are going to get when we differentiate this function right here, and this is what you are going to get when you also differentiate this. So that is the idea. Anytime you are differentiating a polynomial function and a radical function, first, if it is a radical function, convert the radical function to something like this, right? Before you apply the what? The power rule, right? So we will solve more examples combining a lot of functions. But what we are trying to do here is we want to know how to differentiate individual functions. So I know how to differentiate a polynomial function. I know how to differentiate a radical function. Now let's look at the next function that we are coming to talk about. Now we are coming to learn how to differentiate an exponential function, right? Now exponential function comes with two forms, one with the e and one without the e, right? So we are going to learn how to differentiate this, and if you learn how to differentiate this function, then you'll be okay when you are applying the power rule, the quotient rule, the chain rule, because you know how to differentiate an individual function, right? So now let's see how to differentiate e to the power x. Y is equal to e to the power x. I'm going to show you the general way of differentiating e to the power something, so that any function that you see e to the power something, you will just what? Differentiate using what you are going to learn here. So y prime is equal to, this is how we do it. Maintain the function. That is how to differentiate an exponential function. I maintain the function and multiply the function by the derivative of the top. That is the power, right? So this is the base. And then the base here, the reason why I equated this one to constant is you will learn when the base is not constant very soon, right? So when the base is constant, this is the rule that you are going to use to differentiate the function. So I maintain the function, then I differentiate what is on the top. So x prime times length of the base. So that is the idea. Maintain the function, right, which is here, differentiate the power, and then pick length of the base, which is this. That's the reason why I wrote this one power and this one to be the base, right? So this is what you are going to get. Now, what you need to know is, you need to know that, note that length of e to the power 1 is the same as this, and this is equal to 1. And then e to the power length of 1, which is the same as length of, sorry, e to the power length is also equal to 1, right? So this is going to give us ex times, when I differentiate x, we know that when I differentiate s, I'm going to get 1 times length of e from here is equal to 1. So we are going to have times 1, and this is going to give us e to the power x. Now, the idea of this, mostly we omit this here because this is equal to 1. But I just brought this so that we will have it in mind whenever we are differentiating, when the base is not e, but it's just different constant. Let me say 2, 3, or 5, or anything, right? But whenever we are differentiating an exponential function like e, we don't actually see this. We just maintain the function, and then we differentiate the top without thinking about this, because we know that this will be always 1. So this is how we are going to differentiate e to the power x. Now let me add the same thing for y is equal to 2 to the power x. Now it's going to follow the same procedure, but one thing that we are going to learn from here is that the 1 here is not going to be 1. So let's see. The same idea. Y prime will be equal to, maintain the function, which is 2 to the power x, times differentiate the power, which is x, times length of the base, which is 2. So now the length of the base, sorry, now the base is not e, it is what? 2. And we can see that e to the power 2, sorry, length 2 is not 1. As we saw from here that length of e is 1. So that's the reason why here we don't see this here, but here we need to bring it. So mostly when I'm differentiating this, I try to prompt you on this so that you will learn that when this is not e and you are doing it, you are not going to get just this one to be 1, so that you are just going to say, I will maintain the function and differentiate the top, which is going to give you 2 to the power x without the length 2. So this is going to give us 2x times, when I differentiate x, I'm going to get 1 times length 2, and this is going to give us 2x ln 2. So this is what we are going to get at the end of the day. But here we saw that this ln of e is 1. If not, we could have gotten something like e to the power x times ln e, as we saw it here, right? So you can see that ln of the base, ln of the base. But this is equal to 1, so we don't see it from there. So the shortcut way of doing this is that anytime I have e to the power x, I just maintain the function and differentiate the top without thinking about taking the ln of the base, right? But when the base is not e, then you need to have it in mind that you need to take ln of the base, right? Good. So now that we know how to differentiate a ln an exponential function when the base is e and when the base is not e, let's try it here. So what we've learned here is a general way of differentiating the function, right? So you can do it with any function. So you can see that even this one is x squared minus 1, s cubed. You can use the same procedure to do that, right? So now let's try and differentiate the functions there and see what we are going to get at the end of the day, right? So let me just shift this one down, so that now we can take the examples here. Now let's look at the first one. A, f of x is equal to e to the power 2x, right? So what will be f prime of x? F prime of x is equal to e to the power 2x times, then I take the derivative of the top. That's all. So this one, if you know how to do it, like when I take the derivative of the top, what am I going to get? 2. Then you just multiply it by 2. But I will just write d over dx 2x, right? And this will be 2 times. When I differentiate 2x, I'll get 2. And this is going to give us 2e to the power x. So you saw that when we started doing some examples without talking about this rule, we said just when it is a linear function, we just drop what is here down. So 2 here, 2 here. But having in mind that that is not the actual idea, we can bring the coefficient of x in front when we differentiate, when the function here is a linear function. Now, when we take the b, you will see that the general idea is maintain the function and differentiate, not picking the coefficient of the x to multiply the whole function, right? So maintain the function, differentiate the power, and then that is the derivative of an exponential function. So you saw that here I didn't bother myself to multiply it by ln e, because ln e here is 1, right? And under multiplication, 1 is an identity element, so I don't even need it. So that is what I'm going to get for the first one. But let's look at the b. B, gen of x is equal to e to the power x squared minus 1, right? So now what am I going to get when I differentiate? First thing is maintain the function times, then you differentiate the exponent. What is here? So I'm going to have d over dx x squared minus 1. Now here, if you know how to do it, you can just do it straight. For example, this one, if I wanted to do it straight, f prime of x will be, now I maintain the function and then differentiate the top, which is 2. That's all, without writing times this, right? But because I want you to learn how to do it, that's the reason why I bring this one. So when you become good, you can skip some of the steps and then we just write it straight away, right? So this is going to give us e to the power x squared minus 1 times, now when I differentiate x squared, we know that we are going to get 2x, but when I differentiate minus 1, I get 0. So this is what I'm going to get. Then when I multiply, I'm going to have 2x e to the power x squared minus 1. So you see that now if you are picking the coefficient of this to drop it here, you are going to get it wrong. So know the general way of differentiating an exponential function, e to the power something. So this is the general way of doing that, right? This is the general way of doing that. So any function, just go through the same process, maintain the function and differentiate the power. Then that is all, right? That is all. Now let's look at the C. The C, we are going to explore on the second one, when the base is not what? E, right? When the base is not E. So C, we have h of x, which is equal to x 3 to the power minus x squared plus 1. So what will be h prime of x? This is going to be maintain the function, right, times differentiate the exponent, which is negative x squared plus 1. So d over dx of minus x squared plus 1 times, so don't forget here we need to pick ln of the base, right? Because here we know that ln of the base is not going to give us what? 1. So that is the difference between when the base is e and then when the base is not what? E. But it is a constant. That's why I wrote it here. When the base is not e, but it is a constant. For example, we will learn how to differentiate when the base is not a constant. So you can see that here is s, the base is also x, not a constant. We will learn it. But here, when the base is a constant, different from e, then we need to add ln of the base to it. So this is going to give us minus x squared plus 1. Then when I differentiate minus x squared, I'm going to get minus 2x. When I differentiate 1, I'm going to get 0 times ln of 3. So here you don't need to even check it on the calculator. What is a ln of 3? You can just maintain it like that. So this is going to give us minus 2x times minus x squared plus 1 times ln 3. So this will be the final results, right? So if you forget the ln, it means that your final result is going to be this, which is wrong because you need to add ln of 3 because ln of 3 is not equal to 1. This one, our answer should be with ln e, but ln e is 1. So that's the reason why we don't have it there, right? So that is the idea that we were trying to explore. So what I will want you to do is try the D using the same procedure and drop your final results in the comment section. Right. So now we know how to differentiate an polynomial function, radical function. We learn how to differentiate an exponential function when the base is e and when the base is not e. Now let's learn how to differentiate natural log function, natural logarithm, right? So len. So the L here is this, and then the N here is this. So len function. We are come to learn how to differentiate a len function, right? So how do we differentiate a len function? It's very simple. It's very simple. I think I need to show you something here. So when you are differentiating an exponential function, we said maintain the function, multiply it by the derivative of the power. So you can have that thing in mind. If I want to differentiate this, maintain the function, multiply it by the derivative of the power times ln of the base, which also goes with this one. Maintain the function, differentiate the power, and multiply it by the ln of the base, which is here, ln base. Good. Now, let's go through how to differentiate a ln function, right? Or a ln function. So y prime is equal to, here is the general way of differentiating a ln function. So mostly when I see a ln function, I try to put my function in parentheses because of the way I say it. So I'm saying that when you want to differentiate a ln function, 1 divided by what is inside the parentheses. So what is inside the parentheses is x, all times the derivative of what is inside the what? Parentheses. So x prime. Yes. So this is going to give us 1 over x times. When I differentiate x, I get 1. And this is going to give us 1 over x. So that's the reason why we know that when I differentiate ln x, I get 1 over x. Not just like you are just picking 1 over x, like 1 over what is here. If you take that idea, then it means that if I want to differentiate ln of x to the power 3 minus x, then I'll just say is equal to 1 over x to the power 3 minus x. But don't forget, when you finish, you need to multiply it by the derivative of what is inside the what? The parentheses. Right. So that is the way of differentiating a ln function. 1 divided by what is inside the parentheses, all times the derivative of what is inside the what? Parentheses. So now let's look at some few examples that we want to go through together, right? So f of x is equal to ln 2x. So I want to differentiate this. F prime of x is equal to 1 divided by what is inside the parenthesis times, then I will differentiate what is inside the parenthesis. So this is going to give us 1 over 2x times, when I differentiate 2x, what am I going to get? 2, right? Because when I differentiate x, I just get 1. Then this one, fortunate for us, 2 will cancel 2, and I'm going to have 1 over x, which is very nice. Yeah, so this is how we differentiate a ln function. So you see, it's very nice to know how to differentiate, individual functions, so that now when you combine them, like we have two functions which is going with exponential function and ln function, you are differentiating it. All you need to know is learn the type of rule that you are going to use, and you'll be able to go through the process successfully, right? So now let's look at the b. B is gen of x is equal to ln of x squared plus 1. So this is very fun. Gen prime of x will be equal to 1 divided by what is inside the parenthesis times what is inside the parenthesis prime. Very simple. So this is going to be 1 over x squared plus 1 times, when I differentiate what's inside the parenthesis, what am I going to get? 2x, right? Then when I multiply, I'm going to have 2x divided by x squared plus 1. So you see that it's very simple. So now you are going to do the C and also drop your final results in the comment section. So try this one and let's see what you are going to get at the end of the day. Please make sure you put your final results in the comment section. Right. So now we also know how to differentiate a ln function, right? But now let's look at how to differentiate, log function itself. Log function itself. If I have a log function. But now I'll show you something. Now let me go back and show you something here. Now a ln function can also be written as, so y is equal to ln x. Ln x here can also be written as log of x base e. Good. So ln function here can be also written as this. So I will show you the technique that we were using here, that I didn't bring it, with the idea of, we saw that ln of e is equal to 1, right? So anytime I pick the ln of e, I'm just getting 1. So I don't need to even bother myself bringing it, as we saw from when we were differentiating this, right? So I'll show you something very nice here, the reason why we had this. So I'm going to copy this one to the next page. Then I'll show you how we are going to differentiate the ln function. Then we are going to apply it to the log function here. So paste it. Now we just learned that if I want to differentiate y prime of a ln function, it is 1 over what is inside the parenthesis times the derivative of what is inside the parenthesis. But we omitted something. What did we omitted? We omitted the idea that we need to take we need to take ln of the base, which is e, right? So this goes with e. So here we needed to multiply this x here by ln of e. But we saw that ln of e is 1. So there was no, there is no need for us to, bring this one when we are differentiating the ln function. Because when I simplify this, I'm going to have 1 divided by x. Now ln e is 1, and this one will be 1, which is going to give us 1 over x. Good. So the natural log is, because of the base is e, right? But now when we come to with the original log, when the base is not e but it is a, so it's like when we were differentiating the e function, right? We saw that that one will give us 1, but when the base is not 1, then it means that we need to multiply it by the ln of the base. The same idea here, we multiply it by ln of the base, which is e, and we were getting 1, and we saw that this one too was e base, and we need to also multiply it by 1. So that is the idea of what you are going to do here. So the same process here, this is what you are going to do. Now when I want to differentiate a log function to the base a, x, then y prime will be 1 divided by what is inside the parenthesis, but we are going to modify this by times length of the base, which is a, times the derivative of what is inside the parenthesis. So you see that this is going like what we just learned, the length function, but the only thing that we are doing here is we want to multiply the denominator by length of the base. But the other one, the length of the base was e, so that one was giving us 1, so we didn't even bother ourselves showing it. So this is going to give us 1 over x ln a times, when I differentiate x, I'll get 1, and this is going to be 1 over x ln a, right? So as soon as the base is e, let's assume that a is e, you see that if this one is e, this is going to give us 1, and we're going to have 1 over x, which is the idea of differentiating a ln function, right? So let's go through these examples. I think I need to add something here to the power base. Let me see, 4x squared plus 1, right? So now let's go through this process, and then I'll leave the last for you to do it and place your final results in the comment section. So f of x is equal to log of x base 2. So what is f prime of x? 1 divided by what is inside the parenthesis times length of the base, which is 2, times the derivative of x. So this is going to give us 1 divided by x ln 2. Then when I differentiate this one, I'm going to get 1. And this is going to give us 1 over x ln 2. Very simple. So it's always nice for us to learn how to differentiate individual functions, right? So that now when I'm doing the differentiation and they've combined them, I will be able to find my way out. All I need to do is figure out what type of rule am I going to use, because I know how to differentiate an individual function. Let's look at b. B, want to differentiate the n of x is equal to log of base 4 x squared plus 1, right? Yeah. So gn prime of x will be equal to 1 divided by what is inside the parenthesis, so x squared plus 1, times length of the base, which is 4, times I will differentiate what is inside the parenthesis. Very simple. Very, very simple. 1 divided by what is inside the parenthesis, which is here, times length of the base. So you saw that I placed this one in parenthesis, because if you don't place this one in parenthesis and I write it like this, 1 divided by x squared plus 1 times ln x, I might just think of like just this one, just multiplying this, so that my final simplification here will be 1 divided by x squared times ln plus ln x. That is not the right thing. So make sure that always you put your function in parentheses when it is 2 of them. This one I didn't bother myself to put the x into parentheses because it's just one function, right? So make sure you don't do that mistake. So I put this one in parentheses, ln 4. Then when I differentiate the one in the bracket here, I'll have 2x. So my final result is going to be 2x divided by x squared plus 1, which will be ln 4, like this one here. So this will be the final results when I differentiate a log function. So this is how we differentiate a log function, right? So do the last one, which is the C, and place your results in the comment section. So you will learn, I'll do separate video on how to differentiate an exponential function where the base is not what? Constant. Like for example, here we saw that all the base here are constant. So we will learn how to differentiate when y is equal to, let's say, x to the power x, where the base is not constant, like the base is x, and then the top here too is also what? X. So this is how we differentiate this individual function. So we were able to learn how to differentiate a polynomial function, and we said with a polynomial function, all we need to do is we need to use the power rule. Radical function, we need to rewrite it in a form that we can use the power rule. We learn the exponential function when the base is e and then when the base is not e. And then we learned the natural log function, which is ln of x, which is the same as log of x base e, right? And we also learn how to differentiate the log function itself, right? So this will help us when we combine some examples together and we are going to solve it. So in the next video, we are going to combine examples, right? Which is going to feature a polynomial function, radical function, exponential function, length function, and log function. And we are going to apply either the product rule, the exponential rule, or any rule at all to solve it. See you in the next video.